Hello, everybody. I'm Skip Alzheimer. Welcome to the AV Geeks Lunchtime Streaming Show. Um, so we watch old 16 millimeter films, and this is what we just saw was part of the Library of Congress paper print collection, and technically those films first existed on 35 millimeter and were in distribution and were being pirated like crazy. Movie piracy was a big deal in the early 20th century, believe it or not. Uh, unscrutable labs would take prints of film that were being distributed and make their own copy and then do their own distribution and make money off of it without paying the original copyright holder. So it was clear that studios had to figure out a way to protect their intellectual property. And so what they did, because the Library of Congress didn't quite have a way, the Copyright Office didn't quite have a way to deal with moving images. What was done kind of in the interim is they let studios submit prints. So what they would do is they would basically, and this is anecdotal, I could be getting this wrong. I have a film scholar on Facebook, Bucky Grimm, who's watching. He might have to correct me. But they would basically take the film and they would make a print, a paper print that was several frames, more than several frames, probably 20, 30 frames, on 8 by 10 or 10 by whatever size print, and they would submit a big pile of prints that were basically the film frames printed on each frame printed on like a film like a print, a photographic print, and that would be submitted and that would be copyrighted. So that was the way they did it until somebody at Library of Congress, they figured out, like, no, you can actually submit a film print, like the actual thing on a reel, and we'll accept that as copyright. What happened is that those prints were forgotten because those were early, that's the early 20th century. Somebody discovered them and said, hey, what's interesting is a lot of these film prints don't exist anymore. And on film, because they were on nitrate, the company has disappeared, films got beat up, destroyed, whatever. And so someone figured out that they could strip from the paper print and build big rolls of paper print and then run it through what's called an optical printer, and then you would have a camera that would be taking pictures of it on motion picture film, and then they kind of recreated all of these amazing lost films. The quality wasn't great, and for some reason, maybe this was a cost issue, they only shot it to 16 millimeter. Then it looks like Blackhawk licensed it or used it and distributed it because Blackhawk, a lot of early film fans bought Blackhawk prints. And so it's only recently, probably within the last 10 years, that Library of Congress has revisited that collection of the reels of the paper prints that have been cut up, and they're rescanning them at high resolution and doing some post work on them to kind of get them close back to what they were before, and it's really amazing stuff. So, anyways, that's totally geeking out there. That's what we do at AV Geeks. We totally geek out. So, anyways, these I've been scanning films from a fellow collector, Craig Baldwin, and he sent me a bunch of these LOC paper print reconstituted films. So we'll be watching some of those, along with some of the other films that he sent us. In the meantime, I think it's time to learn about honeybees. Honeybees. Enjoy.
These larvae are 3 days old. Until now, they have been fed royal jelly from glands in the mouth of a worker. This worker is opening a honey cell of stored honey to feed the larvae. Workers also make stored pollen into food for the larvae. After the 3rd day, these foods are given to larvae which will develop into workers or drones. Notice how a worker deposits food for this 4-day-old larvae. After 6 days, the larva spins a cocoon. Inside this cocoon, it will change into a full-grown bee. First, the larva sheds its skin and changes into a pupa, as we see here with the action speeded up. The larvae stay in the cocoon for 12 days and develop into adult bees. Then, each bee starts to gnaw its way out of the cocoon and the cell. The head comes out first. It takes a little time and requires some effort. Then, at last, the bee emerges and is ready to do its work in the nest. The first task of the young workers is to feed the larvae in the nest. As they grow older, the workers ventilate the nest by fanning with their wings. Later, they become guards of the nest. A bumblebee accidentally enters. The guards sense that it is a stranger. The bees attack the intruder and sting it to death. But they also die as they try to remove their stings from the body of the victim. Other guards drag the dead bumblebee to the entrance and push it out. In the summertime, when the nest becomes full of eggs and larvae, the workers get ready to raise a new queen. They select a female larva which they will rear to become a queen. They tear apart her cell and enlarge it. Queens are bigger than workers or drones and need larger cells. The workers feed the queen larva royal jelly only. Other bee larvae receive pollen and honey after the 3rd day. The queen larva grows very quickly. After 5.5 days, the workers seal up the queen cell. Inside her cell, the queen larva is immersed in royal jelly. She will change from a grub to a pupa and finally into an adult queen. In the meantime, the old queen and the field bees prepare to leave the nest. Hide the cap over her cell and emerges as a full-grown queen. The new queen has found another queen cell in the nest. She tears the cell apart. This queen larva will die. Here is another adult queen bee just hatching from its cell. The two queens meet and fight a life and death struggle. The one queen stings her rival to death. But the victor does not die because her sting can be removed from her victim. Some workers watch the battle. The field bees, which left the nest with the old queen, settle temporarily on a branch. The nest bees stay with the new queen. Scout bees leave the swarm and look for a place to build a new nest. When the scouts have found a suitable place for a nest, the thousands of bees in the swarm follow them to it. The swarm makes a beeline toward its new home. After the swarm settles, the workers start to build a new comb. These bees are making wax. The wax is secreted by scales on the underside of the abdomen and is scraped off with the sharp hind legs. The worker then takes the wax into her mouth and chews it until it is soft. Many bees working together scoop out the wax dabs and shape them into cells. Watch the bee at the left. These workers are gathering food for the new nest. At the same time, they cross-pollinate the flowers, thereby helping them to produce seeds. Through a magnifying glass, we see a worker gathering food. This is where the bees get the nectar. These are the anthers which contain the pollen. A worker sips nectar from the blossom with its long, sucking mouth and stores it in her body in a honey sac. When the bee returns to the nest, she circles around the cells. This is called the honey dance. Then she brings up the nectar from the honey sac into her mouth. There it is mixed with secretions which change it into honey. She deposits the mixture in a honey cell. When bees visit flowers, they get the powder-like pollen on the hairs of the body. With the combs on its legs, the bee brushes the pollen from its body into the pollen basket on each hind leg. The bee actually packs the pollen into these sacs until they bulge. Flight is a little difficult with such a heavy load. The bee carries the pollen to the nest in these baskets. Back in the nest, the worker dances around doing a pollen jig before she deposits the pollen. She pries off the pollen pellets and packs them tightly into a pollen cell. The bees use pollen to make bees' bread. Extra food is stored here in the comb for the bees that will live through the cold winter season. Throughout the year, worker bees are busy caring for their house of wax. Bees perform two important services. They help to cross-pollinate many kinds of flowers, and they give us honey, which through the ages has been an important food of man.
Man, those early Irpy films that were later acquired by Encyclopedia Britannica always get me, because there's no, like, you know, outro music or even like a summing up of what you just saw. Like a lot of educational films, they kind of recap. But they don't say today we learned, but they recap what you saw. So kind of, you know, re-pinging, well, you just got a lot of information. Let's go back through and revisit. We don't get that with these early Irpy films. They just kind of stop, and if I'm not paying attention, like I'm trying to thread up another film, then I miss what was going on. Here is another Encyclopedia Britannica film, but this is actually by Encyclopedia Britannica and is in color, and I think they're better at this. So here's Electrons at Work. Enjoy.
What is an electron?
An electronic particle is a complete circuit. Electrons flow. An electric current is a flow of electric charges. With electric charges flow in the opposite direction. When another bulb is added to the circuit, more electric charges flow. The basic electric charge is a particle called the electron.
I can't see any electrons.
They're far too small to be seen.
If you can't see them, how do you know they exist?
You can't see the wind, but that's no reason to believe that the wind doesn't exist. You can't see the wind, but you certainly can see things the wind does. What's making this wheel spin? The wind? No, there's no wind blowing inside this glass tube. The wind is turning this wheel. The wind hits against the windmill and makes it turn. Electrons are hitting against the blades of this wheel, making it turn. If we disconnect the power supply that makes the electrons move, the wheel stops turning. Electrons flow away from here. As they move through the tube, they hit against the blades of the wheel. You can't see the electrons, but you can see the effect they have on the wheel. The electrons that hit against the wheel and make it turn must have mass. When an object has mass, it can move other objects by colliding with them. If this wrecking ball didn't have mass, it couldn't exert a force to smash against the wall. If didn't have mass, they couldn't make the wheel turn. This and many other experiments. In order to balance this small weight, you'd have to put this many electrons on the other pan of the balance. Every material there is made up of tiny particles called atoms. This liquid is called copper sulfate. It's partly made up of atoms of copper. These two metal strips are platinum. The copper sulfate has no effect on the platinum strips. Now there is a complete circuit. The battery is acting as a pump, pushing electrons. The bubbling suggests that something is happening inside here. And it was. The right-hand strip of platinum is now covered with a thin layer of copper. The bubbles are on the other side. And now copper atoms are on the left-hand strip of platinum. It's as if electrons were connected to the copper atoms, because when electrons flow in this circuit, copper atoms move too. And in fact, we believe today that all atoms are partly made up of electrons. Balloons are made of atoms. Electrons are connected to atoms. So there are electrons on the two balloons. There are also electrons on the silk scarf. When the balloon is rubbed with a silk scarf, electrons are actually rubbed off the silk onto the balloon. So the silk has a shortage of electrons, and the balloons have extra electrons. Any object that has a shortage of electrons, or any object that has extra electrons, is said to have an electric charge. The two balloons each have extra electrons. That means they both have the same kind of charge. When two objects have the same kind of charge, they repel each other. That means that they push away from each other. We're rubbing electrons off the scarf onto the hanger. Now the hanger has extra electrons. The balloons also have extra electrons. So the balloons and the hanger all have the same kind of charge. Objects with the same kind of charge repel each other. The scarf has a shortage of electrons. Objects with different kinds of charges attract each other. The hairbrush doesn't attract or repel the banana. But what if we could rub some electrons off the cat onto the brush? We can even attract a stream of water. There seem to be electrons in all these materials at least. Electrons are being forced off here and made to travel in a narrow stream down this tube. The other end of the tube is coated with fluorescent paint. Where the stream of electrons hits it, it glows. Apparently, the hanger and the stream of electrons have the same kind of charge because they repel each other. If the stream of electrons inside the tube could be repelled and attracted fast enough and in just the right directions, we could make a picture as complicated as this.
Tomorrow, mostly fair in the west and south portions.
A television picture is made by a stream of electrons that hit against a screen coated with fluorescent paint. If you look through a magnifying glass, you can easily see the lines made by the stream of electrons as it is moved back and forth across the screen at a very high speed.
These cattle have just arrived from ranches in the west.
The electric charges that make the stream of electrons move in the proper way to form a picture are controlled by these electron tubes. Electron tubes act like valves or faucets. They can turn a flow of electrons on and off. They act very quickly. These tubes can turn a flow of electrons on and off 1,000,000 times a second. These are transistors. Transistors can do what electron tubes do, although they do it in a different way. Transistors have the advantage of being very small. The fact that electrons are easy to control makes them an extremely useful move in such complicated machinery as this. This is an electronic computer. The turning wheels are not the important moving parts of the computer. The important moving parts are the electrons themselves moving in the circuits of the machine. Electronic computers are used in science and industry to solve complicated mathematical problems. Let's try this one out on an easy problem. For example, adding this column of numbers together. The column of numbers is written in code on these cards with holes punched in them. It took the electronic computer about 1/millionth of a second to add those numbers together. We haven't proven to you that there are such things as electrons. You haven't seen one, and the effects you have seen could have been caused by something else. But the fact remains that there are many things in the world today that wouldn't exist if there weren't some kind of tiny particle that has mass and that carries an electric charge.
I have my spaghetti lunch here because it is lunchtime. It was a great film. What I love about that series of films is that they do these really fascinating experiments. And what I also love about it is that everything's like hands. There's not as many shots of people's faces, and there's certainly nobody talking. So that's really kind of great in my mind. It's phenomenal. All right, let's see. What do we want to watch? So many options. We'll watch this, Flammable Liquid Fire Safety, and then we'll watch another film from the scanner. I hope it's going to work. It's got some water damage, but we'll give it a shot. Also, Kevin, thank you so much for the coffee. One way you can support AV Geeks is buying us coffee at ko-fi.com/avgeeks. You can also just hit the thumbs up button, the like button, those things. Really kind of great. So anyway, here's Flammable Liquid Safety, Fire Safety. Enjoy.
Flammable liquids, thousands of gallons stored in huge tanks. Modern industry uses flammable liquids in tremendous quantities received in tank cars, tank trucks, and drums. Manufacturing plant that doesn't use dipping, coating, spraying as a solvent, as fuel, or in chemical processes. Why do we have to handle flammable liquids with such great care? Let's answer that question by setting up a demonstration to show the tremendous power in a drum of gasoline. When gasoline or any other low flash point liquid is ignited, it flashes into flame instantly. The intense burning produces tremendous heat. When this heat affects the other drums, something is bound to happen. What you see here is the tremendous power released by only 40 gallons of gasoline, the bursting of a single drum. You can well imagine what the result would be if this uncontrolled power were released inside the buildings of your plant. When flammable liquids become ignited, damage and destruction are inevitable unless the danger has been foreseen and unless adequate fire protection has been provided. We are now getting ready to set off an explosion in a concrete test tunnel. To speed things up, we're going to spray gasoline over warm bricks. Explosions can be just as destructive as fire, or even more so. When the spray hits the warm bricks, it vaporizes and forms an explosive mixture with air, which fills the entire tunnel. One end of the tunnel is a wooden construction. Inside, the explosive mixture is ready to be ignited. When an explosive mixture is ignited, all the energy is released at once. Tremendous pressure develops almost instantly, and the weakest part of the construction gives way. This sort of thing can happen whenever low-flash flammable liquids are left exposed, so they can vaporize into the air. If means are provided for venting, serious structural damage will be prevented. Explosion venting windows, for instance, saved this building by opening automatically and relieving the pressure. But if the pressure is bottled up, as it was in the enclosure around this oven, destruction is bound to be sudden and complete. What are the precautions that we all must keep in mind in dealing with flammable liquids? First of all, make sure there is no source of ignition that could set off a fire or explosion. A spark or a tiny flame is all that's needed to ignite a flammable liquid of low flash point. When the vapors catch fire, the entire surface flashes into flame. Wherever flammable liquids might be exposed, it's absolutely essential to eliminate any chance of sparks or flame. Take smoking, for instance. The man who ignores the no smoking rule is no friend of yours. He risks the safety of the place you work. He endangers your job and may even endanger your life. A moment of carelessness with a lighted match may mean a lifetime of regret. Play safe, obey the rules. Don't smoke or use matches in any way in flammable liquid areas. Static electricity is another common fire cause where flammable liquids or compounds are exposed, as for example at spreaders and coating machines. How does static electricity occur? On a machine like the one we just saw, the static is generated where the cloth leaves the rolls. Let's see what a static spark looks like. Maybe you remember the machine used to demonstrate static electricity in the laboratory. When a sufficient charge is built up, a spark jumps across the air gap. This is the spark that means trouble when it occurs near flammable liquids. Now, let's run the electrodes from the static machine and hold them over a pan of liquid. You're not likely to see the spark when it occurs, but there's no question about the result produced. What's the answer? How can we prevent static sparks at processes where flammable liquids are handled? One way is to humidify the air. This puts a thin and invisible film of moisture on all objects, which drains away the static as soon as it forms. A dangerous charge cannot accumulate. Another way is to provide electrical grounds, so the static will quickly be carried away. First, the machine frame is grounded. Then the spreader knife is grounded to the machine frame. But we still have to take away the static that forms at the rolls. This is done by the use of static neutralizers, of which these are 3 typical examples. The neutralizers are placed at the points where the cloth leaves the roll, as near to the cloth as possible, across the entire width of the cloth, and one end is connected to a ground. What does this grounding accomplish? Suppose we attach a ground wire to one of the electrodes from the static machine. The machine generates static electricity just as it did before, but now we get no spark and no fire. The ground wire carries off the static charge. So to do your part in preventing static fires, if you operate a flammable liquid process, examine the grounds frequently and keep them in good condition. Here is one of the most serious of all ignition sources, the sparks that are given off from cutting and welding torches. You don't need much imagination to guess what will happen when one of these globules comes in contact with a flammable liquid. The effect is instantaneous, and the consequences may be tremendous if large quantities of liquid are involved in an important manufacturing area. Let us take a look at only one of the many fire disasters that have been caused by cutting and welding equipment. The lesson is clear. Never use cutting or welding equipment in such a way that a spark can reach and ignite flammable vapors. Let's now spill a little gasoline to illustrate another common source of ignition, the misuse of electricity. When an ordinary electric lamp is used near flammable liquids, there is always a chance that it will be broken accidentally. Even with a wire guard, an ordinary lamp can still be broken. What you really need is an explosion-proof outer globe so that when the light bulb breaks, no fire will result. Electrical arcs and sparks from any source must be avoided, and that's why in flammable liquid areas, special electrical equipment is needed. You cannot rely for safety on the fact that a liquid has a high flash point. Some of our worst fires have been in heat treating areas where large quench tanks contain hundreds of gallons of oil. Quench oil does not ignite readily unless it is first heated to its flash point. What often happens is that a conveyor gets hung up, a red-hot part remains partly immersed, and the oil heats up. Soon it catches fire. Eventually, as all the oil becomes heated, the fire can become just as intense as if the liquid were gasoline or any other low-flash liquid. Heat from such a fire will buckle steelwork and seriously damage nearby equipment. So wherever high-flash liquids are heated or might accidentally become heated, treat them with the same care as the more easily ignited liquids. These are the vapors given off from a piece of dry ice. Notice how they are heavier than air, settle to the floor, and collect in the pit. Low-flash flammable liquids are continually giving off invisible vapors which act in exactly the same way. It is these vapors, not the liquid, that ignite and burn. This time we will use a piece of waste saturated with gasoline. You cannot see the vapors, but they are settling to the floor and flowing into the pit just as the dry ice vapors did. When they reach the spark plug, fire immediately flashes back to the piece of waste. This simple demonstration shows why it is so dangerous to use flammable liquids exposed to the air, and how, if you do, the unseen vapors are likely to reach a source of ignition and envelop you in a flash of flame. It would be extremely dangerous in a flammable liquid area to permit any vapors to collect. In this demonstration, we've provided ventilating outlets at low points connected to exhaust ducts with a fan continually in operation to draw off the vapors. As the vapor-laden air is removed, it must be replaced with fresh air from intakes located near the ceiling. Efficient ventilation like this makes certain that the atmosphere will be kept free of any dangerous concentration of vapors. When you have to draw gasoline or a solvent from a drum, there's a right and a wrong way to do it. This is the wrong way. Let us see what might happen. An open container could be easily upset and spill its contents. Vapors could ignite from a static spark or any nearby ignition source. Always use a safety container. It doesn't expose a liquid surface, and if upset, it will not spill the contents. A safety faucet should be used, which automatically stops the flow when the hand is taken away. Static sparks can be prevented by grounding. The drum itself must be grounded. And a ground wire must be connected from the drum to the container into which the liquid is drawn. Filling safety cans by hand pumping is the best method of all because it eliminates the leaking and drippage that sometimes occurs when faucets are used. You cannot use just any kind of container if you want to handle flammable liquids safely. Be sure to use an approved safety can. A strong spring cover keeps it tightly shut when not in use. If the can is tipped over accidentally, it will not spill its contents. A flame arrestor screen in the spout protects the contents from ignition. An approved bench can is used in operations that require the washing of small parts. Let's see how a fire in an approved bench can compares to one in an ordinary open can. The bench can produces only a slight flame. The ordinary can lets the gasoline burn freely. Extinguishing the fire in the bench can is simply a matter of flipping the cover into place. If you do any swabbing with a cloth, the plunger type is the can to use. Accidental ignition need cause no concern. The fire is feeble and it soon dies out. A larger size of wash can is sometimes used for cleaning or dipping. The cover is held open by a fusible link. In case of fire, the link melts and the cover drops into position, extinguishing the fire. What are the best extinguishing agents to use on a fire in a tank of flammable liquids? Some extinguishing methods are not only unsuitable, but positively dangerous. A hose stream, for instance, makes the fire worse by spreading it. The gasoline floats on the water and keeps burning. Later, we'll see that the application of water by means of automatic sprinklers is not objectionable and is actually essential for good protection. The ordinary soda acid extinguisher is also unsuitable for flammable liquids. The stream is a water solution and has the same effect as a very small hose stream. There are 3 types of extinguishers that can be used effectively on flammable liquid fires. One is foam, which spreads a blanket over the burning surface and smothers the fire. Another good extinguisher is carbon dioxide, which reduces the oxygen content in the air below the point which is necessary for combustion. A third extinguisher, good for flammable liquid fires, is the dry chemical type, which discharges a cloud of dry, inert powder. So remember, for flammable liquid fires, there are 3 recommended types: foam, carbon dioxide, and dry chemical. Many dipping processes involve such large quantities of flammable liquids that portable extinguishers would be of no use. Fixed piping systems are provided instead. They operate automatically or can be turned on by hand. Take foam, for instance. Here, the foam is discharging from a special outlet mounted at the rim of the tank a few inches above the liquid surface. Eventually, the blanket of foam covers the entire surface and the fire is extinguished. Carbon dioxide also is used through fixed piping systems for the protection of flammable liquid areas or processes. It may be applied directly to tanks by means of special nozzles along the edge or above the tank, or it may be used in small rooms or enclosures where the entire space can be flooded with the gas. The heat of the fire quickly sets off a detector, which operates the automatic dripping mechanism. As the inert gas floods the area, it cuts off the oxygen supply and the fire goes out. Water spray can also be used in pipe systems if the flammable liquid has a high flash point. The oil used as an insulating medium in transformers is an example of a high flash point liquid. It is not easily ignited, but when an electrical breakdown occurs, the intense arcing forces the oil out of the transformer case and ignites it. A fixed system of water spray is the best form of protection for this kind of fire. When the water spray goes into action, it quickly cools the oil below its flash point and the fire goes out. Here is one of a number of fires that have started in flammable liquids and caused great destruction. The question might well be asked, how can we prevent fire disasters like this? The answer is automatic sprinklers. Sprinklers are needed over all areas where flammable liquids are used, regardless of other types of extinguishing systems. Here is a fire in a low flash point flammable liquid. Let's see what happens with the sprinklers in operation. The sprinklers can't be expected to extinguish a fire in a low flash liquid, but they perform 2 very important functions. First, they reduce the intensity of the fire and keep the surroundings cool, thus preventing the fire from igniting any combustible material in the vicinity. And second, they keep the building steelwork cool, thus preventing buckling and collapse. If the process involves a high flash liquid like quench oil, we might well have just as intense a fire, but in this case, the sprinklers will extinguish the fire because the water quickly cools the oil down below its flash point. You've seen the great hazard of flammable liquids. You've seen the great destruction they can cause. Now do your part to safeguard their use. Remember, treat flammable liquids with respect. No smoking, no matches, no open flames. Prevent static sparks. No cutting, no welding. Use safe electrical equipment. Make sure ventilation is operating. Use safety containers. Use the right extinguisher, foam, CO2, dry chemicals. Inspect and maintain extinguishing systems. Make sure automatic sprinklers are ready for action.
The twist drill is the master tool of the mechanical age. 20th century civilization is built around it. The twist drill is generally formed from bar stock. The correct length is cut off and centered in preparation for machining of the shank, the flute, and the margin. Drills were common tools as far as 1100 BC. However, the modern twist drill, with its milled flute, came into existence about 1860. The twist drill is generally formed by milling two equal and opposite spiral grooves in a cylindrical piece of steel. The grooves, or flute, form suitable cutting edges on the cone-shaped end of the drill. The flutes also provide channels for the removal of chips and allow passage for a lubricant to reach the cutting edges. After the drill has been formed, it is heat treated and quenched in an oil bath for hardening. Heat treating is followed by grinding of the margin. Finally, the point is ground. To get out of a drill, the efficiency that is built into it requires some fundamental knowledge of how it should and should not be used. This can best be done by looking at a drill as though it were an assembly of parts. First, there's the tang, then the shank, the body, the flutes, the margin, the body clearance, the web, and the point. The shank of the drill is the part that fits into the rotating device. There are many types of shanks. The tapered shank and the straight shank are most commonly used. The body of the drill is designed according to the type of work it is to perform. This one is for general work. This one for deep holes. The flutes are spiral grooves on opposite sides of the drill. Their junction with the point forms the cutting lips. The flutes provide an escape for chips and a channel for the coolant to reach the work. The web is a tapered column that separates the flutes. It runs from the point to the shank and could be called the backbone of the drill. The web thickness increases toward the shank, as seen in these two cross sections. Here's how the web would appear if it could be removed from the drill. The margin is the leading edge along the flute. The milled portion behind it is called body clearance. Here, only the margins are touching the ring gauge. Body clearance reduces the amount of rubbing surface. The point of the drill is the cone-shaped surface that does the cutting. In review, here are the parts of the drill. The flutes, which terminate at the cutting lips. The margins, which form the full diameter. The body clearance, which reduces the amount of rubbing surface. The dead center or chisel edge. The cutting lips. And the surface of the point, where most drilling troubles begin. Let's find out why. The surface behind the cutting lips must slope away. This is called lip clearance. A slope angle of 8 to 12 degrees is suitable for most work. The angle of lip clearance is increased toward the center of the drill. This is done by making the chisel edge angle 120 to 135 degrees. The angles formed by the cutting lips and the axis of the drill are normally 59 degrees. These angles should always be equal, and the cutting lips must be of equal length. Know the angles: 8 to 12 degrees lip clearance, 120 to 135 degrees chisel edge angle at the center, 59 degrees for the lip angles with cutting lips of equal length. The best method of pointing a drill to these angles is to use a machine pointer when one is available. Machine pointing eliminates guesswork, saves time and money, and lengthens the useful life of the drill. In pointing a drill, never be satisfied until you have checked the angles and dimensions carefully. Precision in pointing a drill will pay rich dividends in its performance. In pointing by hand on a grinding wheel, the operator must have a thorough understanding of the angles and clearances that govern the efficiency of the twist drill. And because points vary for different materials, he must know the characteristics of the material he is going to drill and grind the point accordingly. The next step in efficient drilling is to be sure that the drill is properly held. First, see that the shank and the holder are clean. Dirt or chips will cause the drill to run out. Use a lead or babbitt hammer to seat the drill. If bushings are not used, it is good practice to spot the hole before starting the drill into the work. The twist drill, properly pointed and skillfully used, is the most efficient tool in the machine shop. One way to keep a drill operating efficiently is to handle it with care. Use a drift to remove it from the press in order to avoid damaging the tang. This drill has been properly cared for and is as good as new. But too often the story does not have such a happy ending. Why do so many drills end up in the scrap box long before their time? Let's look into it. First, the point. Here, the angle is correct, but the lips are not of equal length. This drill will produce an oversized hole. The short cutting lip, which is on the left, has been doing most of the work. The drill was supposed to produce a hole the size of the plug gauge. This happens when the cutting lips are of unequal length. The same thing happens when the lips are of equal length, but the angles unequal. Here the left lip has been doing most of the work. The result is an oversized hole. In a combination of these errors, both lips and angles are unequal. This produces an unbalanced condition that will show up in the finished hole. This unbalanced drill actually cuts 2 diameters. The plug gauge indicates the extremes produced by a drill with both lips and angles unequal.
I can check that gear in a minute, so don't touch anything, okay? Hey! Get down from there! Now! Hey! Turn it over! What if it bumped that control by accident? You'd be mincemeat by now. What have I told you? You don't work on equipment when the engine's running.
Well, I told him not to touch anything. All right, I guess I wasn't thinking.
You weren't thinking? You mean you'll work on engines and machinery and not think of your own personal safety? Here. Shake hands with danger.
Shake hands with danger. Meet a man you ought to know. I used to laugh at safety. Now they call me Three-Fingered Joe. I was young and feisty, never did things by the book. Just let me get my toolbox and I'll take myself a look. I climbed up on a dozier with my mechanic's pride. Said, you can keep it running, friend, while I poke around inside. Shake hands with danger, meet a guy you ought to know. I used to laugh at safety, now they call me Three-Fingered Joe. Although I learned a lesson, I forgot it soon enough. The nicks and burns and scratches showed the young ones I was tough. Till another morning I was grinding on some steel. My other hand got careless and fed my skin into the wheel. Shake hands with danger, step right up and say hello. Grinding wheels and metal are what made me Three-Fingered Joe. I've seen mechanics burning, and I've seen them take a fall just to save themselves a minute. I've seen them lose it all. I've watched them courting trouble, seen them take a chance and lose. They get careless for a moment and spend a lifetime with the blues. Shake hands with danger. friends I used to know. Compared to them, I'm lucky to be just Three-Finger Joe.
Yeah, so there you go. I was hoping there was going to be more abuses of the twist drill than uses, but oh well. There you go. So I put a link to the shirt that I'm wearing. This was actually designed by a friend of mine who is at the NC State Library, and it's not official, but it does use the logo that is in the film. Also, thank you for watching and for donating and for thumbs ups and likes and subscribes. Those are great ways to game the algorithm so that we can get more popular and have more bots in the comments. That's really what we're trying to get to, is more bots. If you like what you saw, you can go to ko-fi.com/avgeeks and buy us coffee. We're also working on our Patreon. So patreon.com/avgeeks is a way to support us as well. You can also go to avgeeks.com and see another 24/7 channel that we have. Unfortunately, it doesn't really have comments, so it's just kind of plain stuff like old lunch shows, etc. So if you're looking for, if you feel like, gosh, I just am now waking up and I want to watch more of these films, then you go to avgeeks.com. Speaking of which, so we did last weekend, a couple of days ago, an experiment where we ran 68 hours worth of content, and I would love your advice if you saw it. I've gotten some great feedback about what's important, and one of the things that's important is people really love this show. They love watching it, they love commenting, they love the community, which is you guys, and so kudos. That's really makes me feel good. So this is not going to ever go away. Even if we did a 24-hour show, we would still set aside a lunch, a live lunch. And this will probably happen unless, for some reason, I can't have lunch, which likely will never happen. Anyways, if you saw the 24/7 streaming channel and you have some words for me, I would love to hear them, and I might ask you some follow-up questions as well. It's in the comments. You can email me at avgeeks@gmail.com, and just let me know. Everybody have a great rest of your day. Rewind or the devil will get you. We'll see you tomorrow. Take care.